So let's recap what I did in the last two lectures. I started by talking about computational complexity, and the purpose of that was to say that some problems are fundamentally very hard. If we choose some models and choose to solve those models, we are going against very difficult problems, like when we play with Boltzmann machines and many other similar models in machine learning. Now, you may think that you have a great algorithm that solves all big Boltzmann machines and so on, but you have to be careful and be aware that you're going against fundamental limits unless p equal np. And so be careful with claims when proposing algorithms. This is MCMC sampler will solve every problem to deal with Ising models and so on. Then we moved on to how can we, at least in our field here in feature learning, deep learning, which is focused mainly in this sort of ecological signals, how can we do better despite the fact that some problems are incredibly hard? And we said that we will have to pay attention to nature, because nature is a lot simpler. The space of natural images is much, much smaller than the space of all images. So it is important to use nature as a guideline. Since we were talking about nature, dynamics arose, because dynamics is a very important part of nature. And I argued that dynamics is important not only to be able to design algorithms, to be able to design models and understand how things work, but actually ultimately what the example of stochastic approximation and how we analyze its convergence was about was to say that dynamics and algorithm are actually the same thing. Okay, so physicists would talk about dynamics, we talk about algorithms, but fundamentally your algorithm is following certain dynamics. We analyze convergence like that, and some of those intuitions actually help with actually designing better algorithms. And finally, we moved on to talk about the principle of contrasting in order to learn. So if what you imagine is what you see in the world through some statistical length, which could be that expression that was similar to entropy in the case of maximum likelihood, and it had different expressions. So we saw, for example, for maximum likelihood, in the case of an RBM, it amounts to just essentially contrasting data that you're simulating by following a Markov chain, and data, and we're following a Markov chain simply because that's one way we can do it practically. But those samples could be obtained without following a Markov chain. So the point being, you're contrasting data coming from a sampler with data that you actually see in the world. We saw the principle of contrast of divergence, where you actually just take one step away from the data. That gives you the negative data set with respect to which to contrast. And then we saw also other principles like pseudo-likelihood and ratio matching, which what they do in the binary case is they just flip one variable at a time, and they consider all possible flips. So you're actually only doing very local perturbations of the data when you do that. And so what seems key is then this, figuring out in the design, what seems key in the design of estimators is really figuring out what should you be contrasting against. So I think one could argue there are a great many problems in learning are one-class problems. You're never given the negative labels. So you're told that that's a cat, that's a dog, this web page is about Charlize Theron, and so on. And, but you're not given the negative label as to what the web page is not about. And so it's important in supervised learning to adhere to this principle of contrastive learning as in order to solve one-class problems. And so we saw a very good example this week of Jason Weston, where he demonstrates that actually just by increasing the amount of data using contrasting, they can get excellent results in a wide variety of tasks arising in natural language processing. Now, speaking of contrasting, I had a few questions that I would like to go over quickly. So we saw that in the demo, ratio matching, so some estimators seem to be more robust to noise than others. And a few people asked me about this property of robustness to noise. How can you make an algorithm more robust to noise, and so on. So I'm just going to do something very quickly here. And I'm going to take you back to a very simple, familiar problem. The problem of fitting a line to a bunch of points. And I'm going to illustrate that with 4 plots. OK, so we all know the deal. You have a bunch of points. And we can fit lines to those points. Sometimes it's easier to draw the line first and then draw the point. But that's cheating, at least in the context of a paper. OK, but the problem is that sometimes we encounter this situation. OK, there's that black sheep, that one-off point. And on the web, you get a lot of this. Because if you're dealing with labeling images and so on, using the data that you can find on the web, now and then someone's going to give it a crazy label that you're going to have to deal with. So robustness is a fundamental problem. Now, let's look at this. And so typically, if you're doing least squares, and least squares uses a quadratic laws, what happens is you end up getting a line that will look like this. So your fit will be distorted by this point. Why is that happening? The reason it happens is because let's just project these points. Oops, I meant to say let's take this point here, the center of the line, and I'm going to project the center of the line here. And I'm going to project this point, which is off the line, here. And we're going to look at the loss that we're using here, which is the quadratic loss. Actually, that's almost linear, so that's not going to serve my illustration. Let me try to draw a better quadratic function. Probably an exaggerated quadratic function. Now, the way we measure errors in least squares is by looking at the quadratic error, the squared difference between. So essentially what I'm doing here is a cut. Okay, and so this red curve is really here. And if I draw this sort of thing like this, this is essentially the error that I'm talking about. Okay? So if a point deviates slightly from being along the true model, which would be that green line, you actually get a huge error. Okay? Squared loss basically means your error is increasing quadratically. So this, even though you could have many points here, just that one point that is here is going to give you a huge error. And so what the algorithm does to compensate for that error is actually the line tilts a little bit. And it tries, so this point here, the origin will move a little bit so that all the guys have just a small quadratic error. But we end up with that line, that purple line, which is not quite what we would like. We would like that purple line to actually, we will have, in a way, we want two explanations. We want to say there is a green line and there is an outlier, as opposed to just having one explanation that doesn't really cut it. Now, enter robust statistics. And essentially what we do in robust statistics is we change the loss. So we introduce a loss that will be linear, 0 at one point. There's many other losses you could use, but this is an example that will be useful for us to think about ranking loss later. So we introduce this type of loss, and so if I were to do the same thing here, draw this loss here, what we see is that if the deviations now are only growing linearly. Okay. And in fact, we typically, the center, let's call the center here A, let's call this point B, B, and this is the loss. Oops. And this is your what we typically call XY. So what we see is that beyond a certain point, a certain margin, M, we actually don't incur loss. So the points that are in the middle, they all get fit nicely. If a point goes off, then we only pay linear cost. So when you do this, you will get another fit, but it most likely will be a nice fit, very close to what you had before. Okay, so it's a way of protecting against outliers. This still doesn't give us the two explanations that we want, but at least it gives us one explanation that is robust against this sort of outlier. Now in classification, that was for regression. But for classification, the same is true. In classification, we typically use 0. So if you're doing binary classification, you would use 0, 1 loss. You either get it right or you don't get it right. And so if we plot 0, 1 loss, we essentially get this, so assuming that we're playing with binary variables, plus or minus 1, we would essentially get a loss function that looks like this. Okay? And then the analogous of the hinge in this case, because we're doing classification, we just need one class. The analogous of the hinge the Huber loss would be the hinge loss, which is like this. Okay, it's like the soft thresholding, but the soft thresholding function flipped to the other side. Many other losses are possible. This hinge loss is used a lot in SVMs. It's very popular. But of course, you could use different kinds of losses. So this is basically your deviation, your error. So this would be, I don't know, or the prediction in the case of binary classification. And this is the loss. And of course, you also get things like the exponential loss, which, yeah, we'll go through one. And okay, not the best draw, but an exponential going down. You get exponential loss, you get logistic, the logit loss, and so on. Exponential loss, again, just by looking at the picture, you can tell it's not robust because it's also growing exponentially. And if you use AdaBoost, which is based on the exponential loss, you will find out that AdaBoost will not work well if you have outliers when you're doing classification. And for that purpose, a lot of people have suggested to instead use logistic boosting, or to try new forms of doing boosting that are actually robust. So, but the issue of robustness, extremely important. Whether you're doing bioinformatics, working on the web, you will find outliers. All right, so one more thing related to the last two classes, and it's to do with stochastic approximation. So I mentioned that if you use the learning rate 1 over t, that's actually a good idea because it's easy to get proofs. And that's what I said. I did not say that it's a good idea empirically. In fact, that's also only true because I was making an asymptotic argument. But even with asymptotic stochastic approximation, you can use a fixed learning rate. If you believe you're in a non-stationary distribution where your environment is changing, you would want to use a fixed learning rate in order to be able to adapt. If you're in a convex world where you actually know how many steps you are allowed to go in your stochastic approximation, then there is actually an optimal known learning rate. And I think it's by Nemirovsky. I forget the authors. It's in a paper called Robust Stochastic Programming. What I do recommend is, in the finite case, there is also some very good bounds by Francis Bach and Eric Moline. And in fact, Eric Moline has a beautiful book on, the book is titled Hidden Markov Models, but it actually has a very nice treatment of stochastic approximation and a lot of very nice ideas that we use in machine learning. So yeah, and of course there's adaptive learning rates, there's second order methods, which I imagine you learned about last week, because some of the proponents of second order stochastic approximations were here, people like Nando et al. And so on. All right, so the question of what to contrast then leads us to the framework of max margin. So we want to maximize sort of the difference between the truth and any other possibility. Okay, and with max margin, there's the question then is how you construct the negative set. And I'm going to go over what we would actually want to do. OK, so again, we're going to use a Boltzmann machine. So this is the energy formulation of a Boltzmann machine. By integrating over h, and I will let you go over this exercise, it's possible to get an expression that doesn't involve the h's, that only involves the x's. But now this is a densely connected graph. By integrating the h's, we've broken the structure, and now we have a graph that's fully connected with very large cliques. So our distribution now is quite complex. And it has to be the case because the hidden units were allowing us to be conditionally independent. Once you get rid of the hidden units, you no longer have the conditional independence, so you get direct dependencies. And that's sort of a very important concept. If you want to do modeling, introducing latent variables allows you to simplify your distribution, to break direct dependencies. And it, as was pointed out yesterday, can be used to actually do inference more efficiently. OK, so the way max margin people approach the problem is as follows. And this is typically done in the context of kernel machines and so on, but it also applies with our models. So the idea is you want to find, and this is sort of borrowing from the support vector machine literature, you want to find a set of sparse parameters. So you want to fit the RBM, but you don't want all the parameters to be active. And you could potentially use other forms of sparsity here. But you want to make it such that for any possible realization of the data, and for all your n variables, you want the probability of the data to be greater than or equal to the probability any other possible realization. Okay, you want the data to be the most probable thing. You want to compute the W that makes the data be the most, more probable, because that gives you the most reasonable description of what is going on. Okay, so again, we have here the this would be the world, and this would be the Homer Simpson in my cartoon. Now we have expressions for the probabilities in terms of energies, and so just by taking logs, we can rewrite the constraint, the probability constraint, in terms of energies. So essentially, because if you want to make this more probable, you want to essentially have lower energy for the data. You want to, as Jan LeCun probably explained, you want to go down these basins and put the data at the bottom. Now, what's done in max margin, for now, forget about this term and forget about the etas. To enforce this constraint, I could just say I want the energy of the data to be much lower than the energy of anything else. But alternatively, what I can do is I can introduce a margin, alpha, and that's basically now I'm saying I want the energy of anything else to be greater than or equal to the energy plus alpha. Now, in addition to having a margin, what's typically done is you introduce these slack variables, and you can think of slack variables exactly as the name implies. It's allowing some of the constraints to be relaxed. And these are just useful for optimization. Okay, so now our problem is taking this very sort of the support vector machine flavor. We want to find a sparse solution subject to a margin constraint on the energies. Now this is exponential because we're doing this for all x's. That's for all possible data. And so if you have d binary variables, this space is 2 to the d. You would have to consider all possible ways in which the data could have been corrupted in the binary RBM. Instead, what we can do, and this is one of the things that is typically done, but of course I've mentioned many other things are used. Like you can just corrupt your data, and then you, like for example, if you're, as Jason showed, you can just generate some corrupted data and then try to contrast the energy of the true data against the energy of the corrupted data. And so, but in following the max margin description, what you would want to do is find the minimum over the energies and contrast that with respect to the energy of your data. Okay, so you try to find the best situation and yet be able to contrast it so that you're not doing much worse by modeling the data. Now, doing this in this constrained optimization formulation is often hard. Sometimes it's easier. It depends really on the expressions that you have with the energies, and depends on how you're implementing this on a machine, especially now if you're doing parallel computation. What's typically done, though, often done in support vector machines, is that people will, instead of having this loss here as a constraint, they move this loss to the objective. They add it to the objective, and that's essentially something that probably was covered last week when you had your tutorials on constrained optimization. When you move it to the objective while enforcing a margin, you essentially introduce the hinge loss, which is this sort of the opposite of the rectified loss, which is going down and then 0 to the right. And you essentially try to minimize that loss. And in this case, I've chosen alpha equal to 1 in classification. And as you saw in earlier talks, people often set this alpha to be equal to 1. And so we could formulate the problem now as one of trying to find the optimal, minimize the hinge loss with a quadratic regularizer, and then use as the contrasting term, say, the minimum of the energy. But of course, if instead you use this, instead of using this max margin negative data set, you use any other data set, say data corrupted data set and so on, we're back in the general sort of framework of let's figure out what we should be contrasting against. Optimizing this is actually very hard. Okay. So this principle is really important. And so far, I've only been talking to binary variables. And you might ask what happens in the continuous case. And also been using all these probabilities and so on. And you might say, well, we've seen in the last few lectures that if you just stack a bunch of layers and do backpropagation neural network, there might be no need for probability. So I would like to revisit that discussion. So what I will show next is a connection between, so I'll bring a new estimator called score matching. And I will show how through using this estimator, we can actually map seemingly easily from probability distributions like factored RBMs, the sort of type of complex cell networks that we've heard about, to completely deterministic estimators, essentially neural networks or autoencoders. Okay, again, so we have these probabilistic models. We've seen a few. We've seen the restricted Boltzmann machine. We've seen the factor RBMs. And we can always specify distribution in terms of e to the minus energy divided by some partition function. And again, these problems are very hard because you have to evaluate these partition functions. The normalization constant requires an exponential amount of computations. So with the exact example, it was 2 to the 5. But of course, if you now have 1,000 variables, you now have a 2 to the 1,000 problem, which is a very hard problem. Cost is growing exponentially. Now, I'm going to use now an example which will actually be a Gaussian RBM. So in a Gaussian RBM, my visible units will now be continuous, but the hidden units for now will still be binary. So I still have continuous observations like in an image, but I'm trying to find binary indicators that basically say whether a feature is present or not in the image. And again, in that case, we specify a different energy with a quadratic term and so on. And we can still, for this energy, compute the free energy by integrating out the hidden units. On the other hand, we have these deterministic autoencoders, where you start at the visible data. You go through some encoding to give you a hidden layer. And then you do a decoding to give you, again, a prediction of the visible layer. And then we try to minimize, often, the quadratic difference between these two terms. Other things like cross entropy and so on are possible, but this is sort of one of the popular ways. So that's basically autoencoders. And the question is, how do they relate to each other? And to see that, one way to build these relations is to go to the world of score matching. All right, so and here's a vanilla autoencoder. So typically, as we've seen in many talks here, you go to the hidden units by using sigmoids, and then you project back using linear projections to give you the reconstructions. Now, energy-based models, that is the probabilistic models that I've been talking about, well, they're probabilistic, which some would see as a plus. Not everyone, because some people hate probability, wouldn't see that as a plus. These are undirected. The autoencoders are directed. They're deterministic. The inference here can be slow because you have to solve for this partition function, whereas you might be able to do very fast inference here. The objective function here is, it's interactable because you have this partition function. Another thing that makes the inference slow is that if you have actually multiple layers of RBMs, like a deep Boltzmann machine, and if you want to reconstruct data, you actually have, typically run a Gibbs sampler. And that could take a long time before you can get the reconstructions. But this is sort of feed-forward reconstruction. So you put in the data, go to the hidden, and then go one more layer up, and you have the reconstruction. So it's very fast to do the sort of reconstructions. Now, here's how we can build a connection. So let's look at first at score matching. So it's an idea that was proposed by Apo Hivarinen, and it's a really smart idea. It's, again, a contrasting idea. And what's going to be contrasted in this case is the distribution of the data. And now I will use p tilde to describe the distribution of the data against the distribution of the model. Again, the world is here. Homer Simpson is here. And the sort of ingenious trick of Apo was to take the derivative with respect to the data. Typically we take the derivatives with respect to parameters. He actually goes on this seemingly crazy idea. Let's take the derivative with respect to the data. Now, why would we want to take the derivative with respect to the data? The reason is because if we have a model that's equal to e to the minus f theta of v divided by z of theta. When we take the log of this, so we will have, sorry, I don't have much space here, so I'm going to try to write it here. We will get that the log of the distribution is equal to the free energy, the negative free energy, minus the log of z. Now, what happens when we take the derivative of this guy? It vanishes. It doesn't depend on z. And that's how you get rid of the partition function. It's a very beautiful trick. It's very simple. There's only one catch. I've done this derivative for the model distribution. What about this derivative? So that actually turns out to be very tricky, because you do not, I mean, this, if you have data, would be a bunch of spikes at the data. And if you try to think of the true distribution of the data, well, you don't have it. You don't have that infinite dimensional object. Instead, Apo goes and does a lot of magic, a lot of expansions and so on in his paper, and he ends up with this expression being, in many cases actually, a very good approximation of this. Now, this other expression does not involve p tilde. It doesn't involve the distribution of the data. And so provided that all the assumptions in Apo's work are fine and satisfied, all you need to do is, this is just an empirical expectation. So the empirical expectation will basically, you replace this by just the average over the data. So that's not a problem. And now we just need to compute derivatives. Now we need a first derivative with respect to the data. Then we need a second derivative with respect to the data. And then we will need the derivative with respect to the parameters. There's two ways to do this. The brute force approach is you go to a coffee shop, you drink a lot of coffee, you go back the next day. By the end of it, you have 10 pages of derivatives. And then you go back and you ask your grad student to type it cleanly to make sure you haven't made mistakes. The other approach is you use Theano. And this is exactly when we were doing, when Mark Aurelio and Kevin and all of us were working on this problem. So initially, I did these derivations. A student of mine, David Buchman, went and implemented the gradients and typed it nicely. And the typed version was 10 pages. My scribbles were like a book for the MPOT models and the MCRPMs and so on. And then Kevin comes in and he says, oh, you don't need any of the derivatives because there's this beautiful, beautiful trick called automatic differentiation, and you just use Theano and look how fast. And actually, his code was even faster than using our gradients because we weren't grouping the terms well. So Theano is basically a great tool to use for when dealing with these problems where you have to do lots of differentiation. But then it's possible to do something even cooler here to avoid, instead of going with by these simplifications, it's possible to use some other approximations. And those, I think Joshua already introduced them to you. Did he talk about denoising autoencoders? OK, so I'll just go very quickly over it. So, and here I'm using the notation straight out of Pascal Van Zandt's paper. So actually, I cut these equations from his paper. So we have the empirical PDF of the data, which again is a bunch of spikes placed at the data points. So these Dirac delta masses. So, and then they introduce, or Pascal introduces this noise corrupting term. So in other words, you will center this distribution at the data, and then you will use a variance of, say, sigma that you will also choose. So essentially what we're doing is, instead of using spikes for the distribution of the data, we're going to replace that by kernels. Okay? So we're constructing a smooth approximation of this distribution. The derivatives with respect to the data, the visible units, which in this paper denoted x, will be called psi. And so score matching is essentially this. Is the expectation with respect to the empirical distribution. This is the derivative, which is just a free energy, as we saw in the previous slide. And then this is the sort of the nasty object, because you need to take the derivative with respect to the distribution of the data, and obviously we can't do that. So, but however, if we replace this the set of Dirac masses by this kernel density estimate, then we're in business, because now we can take the derivative of this guy, because it's just the derivative of this Gaussian, and we can do that. And so now we've been able to actually not have to do the simplifications, and we end up with this. And more importantly, we actually got rid of the second derivative, one less derivative. Okay? So you still have to sort of play with now tuning your, now you have to deal with having to have a reasonable density estimator by playing with your sigma and so on. But we've actually, first we got rid of some of the simplifications that Apo had to do before, and we got rid of a derivative. And that's very important computationally. This idea is a beautiful idea. Computationally, I would always advise you to use denoising autoencoders, because it's really neat. OK, so, and this, by the way, we started with energy. We formulated this objective. We started with the energy. We integrated out the hidden units to get the free energy. From the free energy, we got this objective. And then we're here at the end. So basically, this is the usual recipe for going from energies to objectives. You start with the energy, you integrate out the hidden variables, you get the free energy, you apply score matching here, and that gives you now a cost function that you can optimize. And to optimize this, again, use Theano. Let's look at examples now. The Gaussian Bernoulli RPM. So Gaussian visible units, and now I'm turning back to my notation, and the hidden units are binary. When you apply score matching, you end up with this objective function. Okay? And what is the first term? That's just an autoencoder. Okay? That's just the reconstruction error. What is the second term? In this case, we can just interpret it. If you have binary variables, this is just the variance of the binary variables. And then this is, because there's a linear projection, this is the sort of, and essentially if you take variance and you project variance through a linear transformation, you need to square the matrix that you're multiplying that variance with. So you get this, this matrix being squared. And so what you have is, you can think of this as the variance of what you're imagining. So when you do autoencoders, you shouldn't just do reconstruction. But if you want to do what a Gaussian RPM does, you should also be minimizing the variance of the things you're imagining. Okay, so your hallucinations can't be too wild. Otherwise, you're in trouble. Now, I will show in the experiments that if you were to use only this, you would not get nice features. And if you actually add this term, then it regularizes the problem nicely. What is the usefulness of this? The usefulness of this is if you're the kind of person that actually likes probability, because the rules of probability, more than anything, allow us to combine different heuristics. It's the glue that puts big models together, because you follow the rules of probability, and it's very mechanical how to go from, how to add new terms and priors and so on. It's a nice language to integrate different components. And if you like that language, and but you actually want to compute with an autoencoder, then one thing you can do is write your model, your probabilistic model, and provided that you can integrate out the latent variables, then you can sort of follow the recipe of getting the free energy and using score matching to give you an autoencoder. So we've designed an autoencoder without thinking in terms of autoencoders. Of course, this is not the only way, and it often is also a good idea to think in terms of autoencoders, do things deterministically, and that's how interesting things like contrastive autoencoders and so on have appeared. It's really a matter of how you like to derive models and how you like to approach the problem. Probability, of course, has other uses, especially if we're making decisions, as we'll see later. It's important to maintain estimates of uncertainty. OK, so I'm not going to go over the whole math here, but that's basically the set of ugly equations that describe the energy. We see here the complex cells, the squared terms there, and that's the free energy. And that's essentially the equations that describe this MPOT model, which is very similar to the factor RPMs that we had a bunch of lectures earlier this week. And if you apply score matching, you end up with this objective. And again, what we see is we get a first term here which is this phi squared, is just the difference between the visible units and the reconstructions using both covariance. In the case, now we have two kinds of units. We have mean units and covariance units. So you need to use them both to reconstruct. So again, we get a reconstruction error. If you start, we get the standard because of the mean units, we get the same term that we had before for the variance of the mean binary units. But now, because you have these covariance units, you start getting something that's very hard to interpret. Okay, you can interpret as sort of message passing, as variance projecting along two paths and so on. But we found an easier way to interpret all of these different estimators, which is to say you always have a reconstruction error, a squared error. You always have a variance of that error in your expressions, and you will always have something that is curvature that you also need to deal with, the curvature of your error. And that's pretty much for any of these RBM models. When you map it via this score matching to get an objective function, you will, for all energy of all these type of energy models, your objective will always be made out of these three components. So it's important to pay attention in the regularizer to what is the variance and what is the curvature of my distribution. And this is essentially what I imagine Jan talked about during his lectures here, where he's trying to shape the energy. And so the intuition is like this. You have a distribution, you have your data here. The first thing you do is try to put the distribution at the data, but then you also need to change its curvature to make the data much more probable than any other explanations. Okay, so this essentially, it's illustrating very clear the different terms that you need to take into account when you're doing energy-based minimization. And this is just to illustrate what happens with filters. If you just do the square root encoder, you get this. And if you want to get the nice, beautiful filters, you need to add the extra term. And this is using different algorithms, adding that extra term to the. One is using the denoising trick. One is without the denoising trick, showing that they basically do the same thing. But the important message here is that the regularizer actually matters. And some of these regularizers are not intuitive. It's not easy to just come up with those cool regularizers out of thin air. But by following the sort of a probabilistic recipe, we are able to get to them. OK, so that essentially concludes this sort of part of the discussion as to understanding how the principles of contrasting. So we've now seen many ways of contrasting. Score matching does this beautiful trick of contrasting derivatives with respect to the energy of, with respect to the data of the distributions, and that has some very nice tricks. Now, score matching is also consistent. I don't know if anyone's derived a CLT for it, but it shouldn't be a hard exercise because it's an M estimator, and for all. I should say, for all these things that are M estimators, which includes pretty much everything I've talked about, most of what I've talked about, you can actually, there are standard formulas as to how you derive this CLT. So there's generic central limit theorems that you can just take out of books in statistics and apply them to your estimator. So it's very easy to derive the variances so that you can have a ballpark comparison of the different estimators. Now, that's not guaranteed to really tell you what's best because that's only an asymptotic result. So it's important to keep that in mind. Nonetheless, it's one way to look at the problem. OK, so I'm thinking that I'm actually, OK, just going to cover one more thing. And this is sort of related to I've been told you guys are sick of sparse coding because you've been doing sparse coding for 3 weeks. So I'll go and do this very quickly. So how many of you have heard of the Adam Coates Kmeans work? Where so Adam Coates just takes patches, he clusters patches, and then he constructs a feature out of those patches by basically doing the following thing. So the standard K-means is you would construct a feature as in you cluster all your patches. That gives you some centroids, so the clusters. And then for any new data point, you would just measure the distance between that new data point and each of the clusters, and you would pick the cluster that is closest to the point. Okay, so it's just 1 out of k encodings for k-means. A different approach is to actually compute the mean, so compute the distances, compute the mean of the distances, and then compare how far is the point x how far is the point x from the average of all the other points. So you take the distance of x to a cluster, but then what matters is not just the distance to a cluster, but it's also what the average distance between all the points is. Now this will give you now a vector that's not just going to be 1 out of k, but several of these guys will be activated, all the ones for which this average distance is greater than the distance of the point to a cluster. So now you have sort of a distributed representation if these guys are on. And by using this very simple trick, and just by doing whitening, by sort of getting rid of redundancies of the data with center surround filters essentially, they're able to get these beautiful filters, again, in color, nice gabors. And at test time, what they do is essentially, if you have a large image for each of these patches, they compute the distance to each of the clusters, and then they extract the feature vector. The feature vector now has k possibilities. And then they do some pulling on these units to create a feature vector, and that's fed into a classifier. So this is sort of very simple way of doing deep learning. The shocking thing about this is it actually works extremely well, beating some of these, very, deeply thought about models like RBMs and some forms of encoders and so on. Now, it's also possible to take that feature vector and just by squaring distances, doing a little algebra, be able to rewrite it as in this form, as a threshold feature. Okay, something that would look like now this is sort of it's non-differentiable at this point. However, it's possible to make this differentiable, and by smoothing this here, and that essentially gives you what is a rectified unit that is being used a lot in autoencoders. So I think a lot of people have moved to those units because they have many other nice properties. And in fact, the motivation has been different, but the motivation often has been to get better derivatives and for derivatives not to vanish, but that's not the only, as we'll see, that's not the only intuition that gives us these units. So these units are nice. Now, I'll just cut it short and just say that there is an optimization algorithm called proximal gradient. And there's an old book of Bertsekas on parallel optimization. I don't remember the name, but I'll try to get it for after the break. It has a beautiful description of proximal gradient. And of course, Francis Bach, I think, recently has also written some nice tutorials about this. So if you try that, and essentially what that optimization algorithm does is if you have an objective function, it adds a term to the objective function, let's say a quadratic term. You could add many other terms here, but it's constructed in a way such that this term vanishes as you converge this to solution, but this term allows you to make the primal objective function strictly convex, which guarantees that the dual is differentiable, et cetera, the sort of thing you would find in an optimization book. It essentially regularizes the problem very nicely, and you're able to do the optimization. If you apply that optimization algorithm to sparse coding, which has one of these non-differentiable points, because it's an absolute, it has the L1 loss, and you start with all the empty solutions, then the threshold features, which is when x is basically, when you typically do k-means or use just random patches, are just equivalent to one iteration of this algorithm on the sparse coding objective, which I'm not even going to bring. But the main idea, the main point here being that when you propose new algorithms, it's important to think of them carefully and be able to relate them to other techniques that already exist out there. So in comparing, we compare estimators, we should also be comparing what algorithms we're using and so on. And I think I'm going to actually leave it there. And when we come back after the break, we're going to look at time and video. And I'm going to have a lecture which hopefully will be a little bit less dry, because I'm not going to be showing a lot of math, but I'm actually going to show you videos. So, and lots of very cool illusions. So we'll get to play a little bit. OK, see you guys soon.